All right, so we'll open up with remote sensing object recognition machine learning. So we engaged with a contract with a company out of Pittsburgh named CEI and Microsoft. Microsoft actually introduced us with them. And so Microsoft has this objective right now to get users using their Azure Cognitive Services. And so they underwrote a small part of this project. And what the ultimate goal was it was broken down into three different components. Component one was training Azure Cognitive Services to detect trees using Google Street Side imagery. So using the street side imagery to have Azure be able to identify there's a tree there and draw a box around the tree as shown here. Component two was then to take those derived boxes and generate a map of those points, where those trees are located on the earth so we can use GIS systems for it. And then finally, component three is, could we identify ash trees? Would we be able to, after we identify that tree and place it on a map, could we also at least get an ash genus recognition from it? So these three components were like the objectives of the engagement with CEI and Microsoft. So focusing in on component one, the first step was to train the model. And so we had GIS technicians manually tag these images, which just simply put is drawing boxes around trees and tagging them as a tree. And the directions that technician was to draw the box if they could clearly see the root of the tree or the trunk of the tree hitting down into the ground. And so in this case, the technician drew this box, this box, this box, but we opted not to draw ones where there was an obstruction where you couldn't see where the trunk was hitting the ground. These tagged images were then fed into the machine learning model, and then here's some examples of the outputs of the machine learning model. So these are three pictures that were produced. The percentages at the bottom of each picture is its confidence that it was a tree. So the very first image, you can see it was 36% confident that that object off the side of the image was a tree, but 87% confident that that one in the middle was indeed a tree. The next image, it picked up 4 trees, and you can see their level of confidence. And then the last image, we can see some of the risks inherent with this process. Is it was only 42% confident that that outside box was a tree, and then 53.4% confident that that inside box was also a tree. However, we know that that inside box is not actually a tree. Those are just sucker branches growing off the trunk. But we were pretty encouraged in what we saw. We felt pretty confident that object recognition, with some tuning on how we're training it, would be able to identify trees pretty accurately. So then we moved into component 2, which is translating those trees from into a map set. So can we take that center position of that box and extrapolate a latitude, longitude on a map? So what we did first was we used the manually tagged boxes. And so in this image here, using those bottom center boxes, this map represents the data that we were comparing against. This is from the city of Baltimore. The green points are the points that we identify with our field inventory. And the light blue points were the points that were dropped by this calculation. What we can see, though, is some cases here where the same tree might be in multiple photos. So in here we have 396,544, 396,566, but we have 2 blue points for each. And what happened is the picture for this particular tree that was fed into the model actually had both trees in it, and so it generated 2 points. We also have, and you can see that with these photos here. So these are some of the example photos, 2 trees. These are those same 2 trees, just from a different perspective. You can see from the building behind. We also identified that this particular record was about 23.5 feet off from that initial calculation. However, if we go across the street, similar situation, the same tree in multiple photos, we're only about 7 feet off. And so some of the takeaways are, for us, was the proximity to the camera really matters. So if we were to think about the direction that the vehicle was traveling, the Google Street car that was grabbing these photos, these trees were closer, these trees were further. So we recognize that proximity to camera really matters. That's something that we learned. And we also learned the necessity of a deduplication process. Since the same tree might get picked up multiple times in different photos, we needed a mechanism to consolidate those common points into a single location. Here's some examples from using machine learning. So the red points were positions that were fed into the machine learning algorithm. So then these points would have been drawn off of boxes produced by Azure's cognitive services. We opted to only use the boxes that it was 80% more or more confident was a tree. The pink dots are the ones that were placed by the system. And if we were to zoom in a little bit closer on some of these, we can see, like in this case, we have a cluster of 3 pink dots around that 1 green dot. And so again, that's probably a case of that same tree being picked up in multiple images. We have this one here where we didn't get a pink dot at all. So that suggests that the machine learning algorithm was unable to pick out this tree, or if it did, it was less than 80% confident of its tree. And then one more example, which is interesting, that the one before, you would think it has to do with it being behind a car, but in this case, we were able to pick up a few of those trees, and they're even more obstructed by a vehicle. So there's it's difficult to kind of get inside the mind of what the machine learning algorithm is doing, but one of the ways to combat this is by just doing more training, giving it more and more information. After we run the deduplication process, so on the left we have all the pink dots that were calculated, and then on the right are the green dots, the darker green dots. Those are those consolidated points. And then if we were to calculate those, we know in this particular set that we had about 233 trees that should have been derived. And after we run the deduplicate, it comes up with 273. This is to be expected because the machine learning algorithm is going to pick up private trees that we wouldn't have gathered in our normal inventory. And then when we look at the average distance of those deduplicated points to their closest tree point, we're at about 19 feet with a standard deviation of 17. So we're pretty excited about this, but we felt that we need to do better. With only 19 feet average, we weren't sure about one, that makes the deduplication processes questionable, and two, will we erroneously pick up a lot of private trees when we're looking for public trees or vice versa? If we can't be sure of the location of that point, it's hard to overlay public right-of-way data to extrapolate only the publicly owned trees. So we pivoted. We decided to take the information, the budget that was allocated for component 3 and repurpose that into fine-tuning component 2. So that's where we are now. We're working on trying to sharpen that precision for component 2. And after that's completed, then we'll be making choices, strategic choices. Do we continue to engage with CEI? Do we maybe try to develop some of this here in-house? What will be our next steps to get to that genus level recognition? All right, everyone. Thanks for that.